right, let's talk about the opposite effect. Let's talk about humidification. I've got dry air. I'm living in some tepid, arid environment, and I want to add vapor to the water. This is on page 1118 of your textbook. I'm going to draw a very similar conduit, except this time I have an entry at the top, an inlet at the top. So this is going to be an inlet, and an exit. So now I have at state 1 some atmospheric air entering at state 1. It has all its associated properties, but here's a key thing to note. The relative humidity has to be less than 100%. I can't add more, just as our bucket kind of explanation in the previous slide, I can't add any more humidity if the bucket's already full. So there has to be room left in the bucket in order to add humidity to the air. So now at state 1, I have, we call that subscript W, I am injecting some type of liquid water or steam at some temperature and some mass flow rate. Now, whether it's liquid or steam is important because that's going to affect where you go on your psychrometric chart. I'm going to exit at state 2, and how it exits state 2 is relative to whether I'm putting in liquid, water, or steam. If I'm injecting steam, so it's hot steam going into the atmospheric air, obviously going to increase the temperature. The temperature at state 2 will be greater than temperature at state 1. If I'm injecting water, the temperature is going to cool. That's a cooling with humidification process. That's because that latent heat of vaporization, that energy from the atmospheric air entering at 1 is going to go into that water, liquid water, to turn it into vapor, thereby cooling the atmospheric air, and it comes out at state 2 at a lower temperature. I'll show you this on a psychrometric chart in a second. My humidity ratio obviously increases because I'm filling up the buckets. I'm adding more vapor to the water, to the air. My relative humidity is going to be dependent on the temperature, the state that it exits at state 2, and that depends on whether I'm adding steam or water. I'll show you that on a chart here in a second. My wet bulb temperature variation depends on whether I'm adding steam or water as well. But my mass flow to dry air hasn't changed. I haven't done anything to the dry air, but my mass flow to the vapor, regardless of whether it's water or steam, is going to increase because I'm filling up those buckets. So conservation of mass in this case would tell me that my mass flow rate at 2 of the vapor is equal to the mass flow of the vapor at 1 plus the mass flow of whatever water or steam I added into my system, so the conservation of mass remains true. Let's look at this on our psychrometric chart. So I have some state 1. The first scenario I'll show you is we add steam. We add hot steam. So I add hot steam and I increase the relative humidity. I increase the humidity ratio as well. You see I've added, I filled up the buckets, and based on the fact I added steam, my temperature has increased, and thereby that affected my my mixture volume, my volume cubic meters per kilogram dry air. It affected my enthalpies, and in fact, your enthalpies are how you're going to fix state 2. You're going to use conservation of energy, and I'll show you how to do that in another video. Conservation of energy, if you know the temperature of the steam, and this is regardless of whether it's steam or water. If you know the state using your steam tables, you know the enthalpy associated with that, you know state 1, you know the mixture enthalpy associated with that because you can fix it, you can solve the conservation of energy equation for the mixture enthalpy at state 2, and that'll determine whether it's increased the temperature and where this state lies, whether it's 2 or if I add cooling water, 2 prime. So in this case, I've added water. Because I added liquid water, it's decreased the temperature because that energy had to go into vaporizing that water. It has also increased my relative humidity, but it's changed basically the carrying capacity, whether it's hotter or colder, how big those buckets are. So obviously the cooler it is, the smaller the buckets, the higher the humidity ratio, the higher the relative humidity, even if it's at the same humidity ratio for cooler water versus hot. Let's look at a very special case. This is called evaporative cooling. So this is humidification, but we're specifying that we're not adding steam, we're adding liquid water. So everything else stays the same, but I want to highlight on the key differences from this versus a normal humidification process. Humidification process is very general, very broad. This is a very specific case, and this is important to read these details in your problems. In this case, I'm injecting water, and that water is at the adiabatic saturation temperature. Now, again, as I stated, this is on page 11-20, and as I stated, the air is providing energy, the latent heat of vaporization, to evaporate the liquid, and it becomes cooler. Now, here's the key. If it's evaporative cooling, so I'm injecting water at the adiabatic saturation temperature, I'm cooling, but I'm maintaining a constant wet bulb temperature. temperature, and that's very important. I'm maintaining a constant wet bulb temperature. Remember, your wet bulb temperature is the lowest temperature that the atmospheric air could achieve using only evaporative cooling, and that's exactly what we're doing. We could evaporate it, use evaporative cooling all the way to 100% relative humidity, but we can do some intermediate steps as well, and I'll show you that in a psychrometric diagram here in a second. Let's focus on some of these key differences between this and a generic humidification process. My temperature, obviously, if I'm cooling using evaporative cooling, my temperature at state 2 is going to be less than my temperature it entered at state 1. My relative humidity is going to increase because my bucket carrying capacity has decreased, right? And I've also increased the vapor as well. That's also going to increase the relative humidity. So my bucket size is shrinking, but I'm also adding vapor, and I can do that all the way until I'm 100% saturated. And here's the key detail: my wet bulb temperature remains constant. That's important when you're using your psychrometric diagram. So let's look at the psychrometric diagram. So I picked some arbitrary state 1 at a very low relative and absolute humidity or humidity ratio. And using evaporative cooling, I have increased both the humidity ratio and the relative humidity, but I've done so at a constant wet bulb temperature to state 2 to get my new dry bulb temperature. So usually that's how I'd fix it. I know what dry bulb temperature I'm going to, or I say that I'm going to do it all the way to saturation, and I follow a line of constant wet bulb temperature. Remember, these are these diagonal lines as demonstrated here above. Okay, last air conditioning process. Then we get into air conditioning problems. We'll kind of combine bits and pieces of each one of these. This is called adiabatic mixing, and this is on page 11-22 of your textbook. Now in this case, I have two separate inlets that are going to combine, they're going to mix, and they're going to do so adiabatically. Now is there heat transfer between each of these flows? Yes, but there's no heat transfer in and out of my control volume. That's why we say it's adiabatic mixing. So let's say I have some mass flow rate of atmospheric air entering at state 1, and I have some mass, it has its associated properties, and I have some mass flow rate of air at state 2 from another conduit. They're going to merge together, and it has its associated properties. Now state 1 and state 2 don't have to be at different temperatures. They could be at the same temperature with different humidities or some differences, but they're not the same air. They have different properties. Okay, I like to do this with the hot and cold because it's easier to demonstrate, but they don't have to be at different temperatures. 2 doesn't have to be colder than 1. This is just very generic, but it's easier to see this way. They're going to mix and they're going to exit at state 3. And at state 3, it's going to have its very own set of properties based on how these mix and based on what the properties are of 1 and 2. I want to focus on this slide on conservation of mass. There's a key thing with conservation of mass. For conservation of mass, you would agree that it tells me what goes in has to go out. So the mass flow rate at 3 of the atmospheric air, of that total dry air vapor mixture, is equal to the sum of the mass flow rate of the atmospheric air and the mass flow rate at 1 and the mass flow rate of the atmospheric air at 2. I could break this down further and say that the mass flow rate of the air of the dry air at 3 is the sum of the mass flow rates of just the dry air from 1 and 2, and respectively the mass flow rate of the vapor by itself at state 3 is equal to the summation of the mass flow rate of the vapors of 1 and 2. And that's very important. We come up with some relationships on how we're going to fix state 3, which I'm going to show you now on this next psychrometric chart. So I pick some state 1, and I'm going to fix state 1 on my psychrometric chart. Remember, this is all at atmospheric pressure, so I need to have 2 other properties. So let's say I have 2 properties that I can fix this state. I need to have 2 other properties to fix state 2. So the question lies, well, where is state 3? Well, that depends on the properties of state 1 and state 2 and on their mass flow rates. So how do I fix state 3? Well, the first thing I'm going to do is connect state 1 and state 2 by a line. Now that I have them connected by a line, I know state 3 has to fall somewhere on the line, has to fall in between these if I'm mixing the 2 together. Where does it fall between those 2 lines? Well, there's 2 methods to figure that out. One is using humidity ratio, the other is enthalpy. So one's using conservation of mass, the other using conservation of energy, the first law of thermodynamics. Let's look at using conservation of mass first. Based on the fact, those conservation of mass relationships I showed you in the previous slide, and the fact that the mass flow rate of the vapor times is equal to the mass flow rate of the dry air times the humidity ratio, I can substitute that into my conservation of mass for the vapor, and I can solve for the humidity ratio at state 3. So that requires me to know the humidity ratio at 1, 2, and the mass flow rates of the dry air at 1 and 2, and the mass flow rate of the dry air at 3. But don't forget, due to conservation of mass, I know that the mass flow rate of the dry air at 3 is equal to the mass flow rate of the dry air at 1 and the mass flow rate of the dry air at 2. So I can use this form of the equation, just realizing that this is simply the sum of the mass flow rates of dry air at 1 and 2. From there, I can fix the humidity ratio at 3, and I draw a straight line of that humidity ratio at 3 across, and where that intersects the lines I drew between 1 and 2, well, that's state 3. That's where state 3 lies. Let's say I can't solve it that way. There's something I don't know. I can also use conservation of energy and use the mixture enthalpy to fix state 3. So we have this relationship derived from the first law, where we say the enthalpy at state 3, the mixture enthalpy at state 3, is equal to the mass flow rate of the dry air times the mixture enthalpy at state 1 plus the mass flow rate of the dry air at state 2 times the mixture enthalpy at state 2, all divided by the mass flow rate of the dry air at state 3. And that's simply conservation of mass. Conservation of energy, the first law of thermodynamics. Again, I can rearrange that knowing the fact that, or substitute in for mass flow rate at dry air at 3, the fact that it's the summation of the mass flow rate of the dry air at 1 and 2. From that, I can solve for the mixture enthalpy at 3, draw a line down from there, and I can fix state 3. Now, I arbitrarily pick these points. I don't know if these mathematically work out. This is just for demonstration purposes only. Those are the two ways that you can fix state 3 if you have a mixture. You have to plot state 1, plot state 2, connect them by a line, and then use some relationships that you know. And you're going to have to obviously get the humidity ratios or the mixture enthalpies off of this psychrometric diagram where you plotted 1 and 2, substitute them into the equation, solve for 3, and then use that on the psychrometric diagram to fix it.